Carbohydrates. We started looking at carbohydrates. We talked about the monosaccharides, and we said monosaccharides we can name them depending with the number of carbon atoms that they have. We have got the trioses, we have got the pentoses, we also have the hexoses, at least of importance. Now, let's first quickly mention the hexose sugars, and then we can now talk about the disaccharides and the polysaccharides. Now, when it comes to the hexose sugars, from the name hexose, these are sugars that have got 6 carbons. That's the meaning of hexose. 6 carbons. Remember the general formula for monosaccharide is CnH2n H, and so that is CnH2nOn. Okay, so meaning that hexose, since they have got 6 carbon, their formula is going to be C6H12 and then O6. So those are the ones. Now, on the hexo sugars of importance, what we need to know is glucose, galactose, and so we have got glucose and galactose and also fructose. These are the main three ones we need to know. So starting with glucose, which is a very common sugar, of course, the most common we can say. What should we know about this? We need to know the structure and, of course, the importance. Why glucose? So, glucose is also known as grape sugar. It is a simple monosaccharide which is found in plants, and it is an important product that will come from photosynthesis. In respiration, we are going to be using down glucose. In photosynthesis, we'll be producing glucose, and photosynthesis, we know that occurs in green plants. We need to know again, remember when we talked about the functional groups of carbohydrates, we said that they can either be can either be aldehydes or a ketone. Glucose, the open chain of glucose is actually an aldehyde. The functional group is at the end of the chain like that. And then at the end here, I'm going to put CH2OH. So you can see there's carbon number 1 here, and then there's carbon number 6. I've used 2 carbons, so I'm remaining with 4 carbons. Those 4 carbons, I'll put 1 here, 2, 3, and 4. Now of glucose, what we need to know is you are going to have OH here. Look at how they are changing. I've got OH here, and then you have got OH here, and then you have got OH here and here. So they make like an S. It goes like this if you follow it. Please take note of that. It's very important to help you to differentiate it from galactose. You can see that the OHs go like this. It's like an S which they make. And then the rest of the atoms will be carbon atoms. H here, H here, and H here. When you look at carbon number 4, this one, you can see the OH is on the what? On the right side, right? When the OH is on the right side there, this is known as a D-glucose. Or you can just say where the OHs are mostly, where they are a lot, that's on the right side. So that is D. If they are on the left side, that would be L. So this is known as D-glucose. So for L, just swap these two, swap these two, swap these two, swap these two, swap everything. That will give you L glucose. It's only D-glucose that can form a ring. And so what happens is that, just like we talked about for the pentoses, the second from last carbon, this one, actually, this group, second from last, is going to go and interact with carbon number 1. But it's not specifically that is carbon number 1, but it is supposed to be the carbon containing the functional group, and we call that carbon a anomeric carbon. And it just comes to be that for glucose, carbon number 1 is the anomeric carbon. So when these react, what you are going to end up forming will be a ring. So I'm going to write it like this. Look at the kind of ring that we are forming. It's different from the ring that we formed when we are making the pentose sugars. because that one was looking like a pentagon and we called it a pyranose ring, the furanose ring. This is a pyranose. So this is what happens. And look at this. These molecules that you see this side will be appearing down when you are forming the ring. Carbon number 1 is going to be here. So at carbon number 1, you can see this OH. The OH can either be on top or it can be down. And wherever you see the oxygen, that means that's where carbon number 1 is. So never say this is carbon number 1 because that's not where the oxygen is. So that's carbon number 1 and carbon number 2. Even when you number this one, this is 1, 2, 3, 4, 5, and 6. So carbon number 2, can you see that OH is down? So here, OH is going to be down, and then H is going to be on top. Carbon number 3, can you see that H is the one which is down? And then OH is going to be on top. I've said that what is this side is what is going to be down. And then carbon number 4, which is going to be here, we are going to have the OH. Okay, carbon 1, 2, 3, 4. We are going to also have OH there. We are going to put OH down and then H on top. Carbon number 5, which is the second from last carbon, you can see there's going to be this hydrogen, and then you are going to have this group here, okay, on that carbon. So we're going to have the hydrogen, and then we're going to have the CH2OH. These same things will be the same for this one. Just write it the same. The only difference is carbon number 1. So what does that difference make? So the way you can see it like this, when the OH is on top, we call that as a beta molecule. So this is known as beta D glucose. But because of the way the molecule is looking, it is looking like an hexagon. We can also call this as beta D glucopyranose. Pyranose. This is a pyranose ring. This is how it looks like. A furanose ring, you can see the way the deoxyribose was. You can see the way the ring is looking. It's a 5-membered ring. That's a pyranose. A furanose looks like this. And then this is this one, because the OH is down at carbon number 1. This is what? This is an alpha molecule. So this is alpha D glucose, also known as alpha D glucopyranose. Alpha D glucopyranose. Okay, so this is the molecule. It's important for us to understand the way we are drawing these molecules, because they can come just like this in the exam and they'll ask you to be able to identify them. That is why I bother to explain how the molecules are coming about, because if you at least understand how they're coming about, you'll be able to remember, other than if you just want to master, right? So this is glucose. And then we can talk about another molecule. Let's talk about, okay, I only have one page here. So I can mention, because it's going to be the same way with galactose. Let me just put here glucose. What's the difference between glucose and galactose? Galactose is opposite on one carbon, and that is at carbon number 4. Can you see this carbon number 4 here? If you just swap these, that forms galactose. And specifically for this one, it is going to be D-galactose. So the way galactose will look is that OH will be here, OH will be here, another OH will be here, this will be H. And then it will go like this. Can you see how the OHs are following each other? They are making like a C. That is how you know that that molecule is not glucose, but galactose. Very easy there. Please make sure that you don't forget that. Glucose and galactose are actually isomers of each other. They are only different at one carbon. Okay, only different. So let me now mention properly. When you're talking about monosaccharides, monosaccharides can be isomers of each other, and you have got what we call structural isomers and stereoisomers. So, for example, galactose and glucose. Glucose and galactose are stereoisomers. What do we mean by them being stereoisomers? The way they differ is just on they have got the same formula, even the structure is the same, but the way atoms are arranged in space is different. For example, at carbon number 4 here, glucose, this is carbon number 4. Glucose, OH is down. But when you look at a molecule like this where you see OH on top, just know that that is galactose at carbon number 4. Because at carbon number 4, they swap. That's the meaning of stereoisomers. They only differ in space. But when you look at glucose and another hexose sugar, which we go fructose, these ones are actually known as the structural isomers. Why are they structural isomers? Because they totally have got different structures. Glucose is an aldose sugar. Same with galactose. These two are aldose sugars. But when you look at fructose, it is not an aldose sugar. Instead, it is a ketose sugar. Okay, that's a difference. So now let's talk about the structure for fructose. So when we look at the way fructose is, as I've already said, fructose is an not an aldehyde. Instead, it's a ketose sugar. So even the way the structure is going to be different. So fructose, the functional group, is not at carbon number 1. Instead, it's at carbon number 2. So the way the molecule is like this. At the end, you have got CH2, OH. The other end, you also have CH2, OH. And then at this carbon, carbon number 2, that's where everything becomes different. This is where a double bond with oxygen is going to be. So I've used up how many carbons? 1, this one, 2 in double bond, 3, the one down. So I'm remaining with 3. So I can put here 1, 2, 3. Okay, like that. So just like the molecule is not different from glucose. Remember glucose we said that we make an S, right? Something like this. If you have got OH here, then you are going to have OH here at carbon this is carbon number 2, this is number 3. Carbon number 4, this side we said there will be OH, and carbon number 5 we said there will be OH. So be carbon number 1, carbon number 2, carbon number 3, number 4, number 5, and number 6. The same way glucose was at carbon number 3, the OH is still going to be the opposite. It's supposed to be more the same. Okay. Carbon number 5, OH is supposed to be this side, right? For glucose, as I've shown. Even here. And then the hydrogens are this side. But at carbon number 3, remember OH is supposed to be this side. The same way glucose was. The only thing is that at carbon number 2, we don't have OH there because that's where the double bond is. This is a molecule of fructose, and I've shown you that so that it is not be a mastering. In case it comes, you'll be able to identify. The other thing you need to know is, again, this can form a ring. And the ring that is formed is because the second from last carbon reacts with the anomeric carbon. The carbon contains the functional group. Second from last carbon is still this carbon. But the carbon contained in the functional group is not carbon number 1, but instead it's carbon number 2. Please take note of that. It's always the second from last carbon with the carbon contained in the functional group. And the functional group for fructose is carbon number 2. So that is what is going to happen. This one reacts there. And when this reacts, what are we going to see in this case? The molecule that forms is similar to the molecule that we formed when we are dealing with pentose sugars. It is also a furanose. It is a it is a ring that looks like a pentagon. So again, we can have two. I can put them like this. Yes, please. So the only thing that you need to know is that fructose is the only Hexose sugar that appears in this shape. The rest of the Hexose sugars will be appearing in this shape, and that's glucose and galactose. This is a furanose. This is a this is a paranose. This is a furanose. It's only fructose which appears as a furanose, and the pentose sugars, but the rest will be paranose. Is that okay? So for this one, carbon number one, you can have CH2 OH on top. You can see carbon number one is this one. That's a CH2OH. But then this OH that has come when this reaction is happening with carbon number one, it can either be on top or down. So it can be either on top or down. The difference with these others is that at carbon number one we are counting was this one. But here carbon number one we are counting is this one. So please make sure that you take note of that. But how are you going to know which one is carbon number one? Because the last carbon is also going to have CH2OH. This one here. So we're going to see it here, CH2OH. Even here, CH2OH. But the difference is that this hydrogen is the one which will be exchanging. Hydrogen can either be down. Actually, the hydrogen will be down, yes. So how you know that this is carbon number one when it comes to fructose is that carbon number one is going to be opposite to the OH. So if you look at this carbon, it's opposite to H. So it's not carbon number one, it's actually carbon number six. So that's how you can identify the carbon number one for this molecule. And then the rest, can you see that carbon number? So this is carbon number one, this is carbon number two, this is carbon number three here. Can you see that carbon number three, H is down, this one, and then OH is going to be on top. Carbon number four, OH is down, and then H is on top. That is done, and that will be the same way with this one. And again for this one, every time you have got OH being down, that is an alpha molecule. Okay, OH being down is alpha. So this is going to be alpha D fructose. Remember I said that it's only the D form of a molecule that can form a ring. So you can't have alpha L fructose. No, the L form doesn't form a ring. We can also call it as alpha D fruct. Remember this is a furanose, so we can say fructofuranose. When OH is on top, that's a beta molecule. So this is beta D fructose, also known as beta D fructofuranose. So yes, please. Yes. So for the L, it doesn't exist. There is no even glucose. There is no alpha L glucose, alpha L ribose. No, the L form does not form a ring. It's only the D form that forms a ring. So this is the structure for fructose. So fructose is also known as fruit sugar, and it is a reducing agent also. So all monosaccharides are reducing agents. The reason as to why they are reducing agents is because of the functional group. Any molecule whose functional group is exposed can reduce other substances. That's why we call them reducing agents. So this is the fructose, and this is how you can write their forms. Fructose is a structural isomer of glucose because they have got totally different structures. It's actually a ketone. Okay, it's a ketose sugar. Why is it a ketose? Because the functional group is not a compound number 1.